Over the past several decades, our energy consumption needs have grown dramatically while our production levels have remained relatively constant. The United States has relied heavily on foreign imports to meet our fossil fuel needs. However, with oil and gas prices steadily rising, it will soon become economically necessary for us to utilize alternative sources of energy. Many scientists have made finding these alternative energy sources their primary goal. Methanol has received a great deal of attention in recent years for its potential as an alternative fuel source. Methanol is an attractive option because it can be derived not only from fossil fuels, but also from municipal waste, wood, and other biomass. Another attractive feature of methanol is that when it is combined with steam, it can react to form carbon dioxide and hydrogen gas, another known clean energy source. Furthermore, it is well known that the addition of a metal catalyst makes this reaction more efficient. Researchers in the Sykes group at Tufts University have been intrigued by the question of what makes a good catalyst. We have made the copper-palladium alloy system the focus of our study. In 1981, a new type of microscope called the scanning tunneling microscope, or STM, was invented. During STM operation, an atomically sharp conductive tip is brought within a nanometer of a conductive surface. A voltage is then applied between the tip and the surface, causing electrons to jump from the tip to the surface in a process called tunneling. The result is a small electrical current called the tunneling current. A circuit called the feedback loop keeps the tunneling current constant by adjusting the distance between the tip and the surface, and an image of the surface is generated by plotting the height of the tip as it scans over the surface. Because the STM image originates from an electrical current, the image contains information about both the topography and the electrical conductance of the sample surface. Here we see an actual STM image of a clean copper surface in which two step edges are clearly visible. If we zoom in on our copper surface, it is quite easy to identify individual copper atoms. Real-time data collection and analysis are performed using two-dimensional images. Using this approach, we are still able to identify individual copper atoms, as well as see how they are arranged with respect to one another on the copper surface. If our copper surface is modified with a very small amount of palladium and hydrogen is then added to the surface, the hydrogen will image as a dark depression or a black dot. Due to hydrogen's relatively weak interaction with the metal surface, it is free to move around, and this motion can be captured through a series of images taken one after the other. These images were acquired at 7 Kelvin or minus 266 degrees Celsius. It is interesting to note that even at such low temperatures, the black hydrogen atoms still have enough energy to move around on the copper-palladium surface. Being able to study how hydrogen interacts with our copper-palladium surface will lead us to a better understanding of what makes it and similar metal catalysts ideal for the methanol reformation reaction. We can also begin to understand how to improve existing catalysts or even develop new ones, thus advancing us towards our goals of energy independence and clean energy sources.